Hi guys, me from the future. I'm actually going to start this one off a little different. I'm colorblind, so like you look at a solution, you say that's green, and I'm like, I mean, I kind of see that. I will be honest that the blues and the yellows very easy to tell apart. The greens and the blues and the yellows still pretty easy to tell apart. It's phenolphthalein every time. It's like, is the solution clear or is it very, very light pink? I have no idea. In college, I had to do a titration in the reverse direction, going from pink to colorless. And I remember distinctly holding up the flask and saying, is this colorless? And they went, no, that's bright pink. How? I hope the video doesn't suffer too much because I can't show it in front of you, and because I'm colorblind, I kind of shied away from the colors a little bit. Hi. Today we're going to continue on acids and bases into the next topic. We're going to consider two solutions, pH of 2, pH of 8. I'm going to give you a minute, pause the video, think about it, run some calculations. For a pH of 2, the H plus concentration is 10 to the negative 2 molar. For a pH of 8, 10 to the negative 8th molar. So between which the pH of 2 has the larger hydronium ion concentration, and the difference between them, all you have to do is divide one by the other and you'll get an answer. Either 10 to the negative 2 over 10 to the negative 8th, or 10 to the negative 8th over 10 to the negative 2. I would suggest the first one. This is, your answer here is going to be 10 to the 6th. This will be 10 to the negative 6th. But either way, the difference in the hydronium ion concentration between solution 1 and solution 2 is a million. One of the solutions is a million times more concentrated H plus than the other. That's why we use pH. It's a difference of 6 in the numbers, 0 to 14. The difference between 0 to 14 is 100 trillion times when you're considering a log-based scale. And because those are just the solutions that you see in biological life, and you can go even farther beyond that, it's good to have something that tamps it down into 0 to 14 as a range. The picture on your left is hydrangeas. They're a flower that, interestingly, the color of the hydrangeas varies based on the acidity level of the soil. On your right, you have a picture of something else that's purple, red cabbage. On the top, we have a 1 molar solution of hydrochloric acid on the left of that cabbage picture. And on the right, it's a 1 molar solution of sodium hydroxide. Both cases, it seems to be that both substances contain something that is not just sensitive to pH in terms of like chemistry, but it's sensitive to pH in terms of color. And I think that's going to be our guiding question for today. Though they're both purple, we can see very clearly that the hydrangea purple color turns into a blue versus a pink, and then the cabbage purple color actually turns into a red versus a yellow. And this is kind of neat because in the middle you get a lot of blues, pinks, and greens. Now, an indicator is a very special subset of a chemical compound. Specifically, indicators are chemical compounds, colorful, and able to change color in response to pH. The idea being, looking at these substances up above, what we have here is, well, I put a lot of information in this slide. It's actually catching me off guard. On your bottom left, you'll see table M from the reference tables. That's the common acid-base indicators, the ones that you're responsible for knowing about for the regions. There are a lot more. In fact, for example, whatever is active in hydrangeas and whatever is active in the cabbage, that's not on the list. There's more. Many fruit juices have something in it that act as an indicator, which is kind of neat. But these are the 6 that the New York State gives you to work with. They give them to you so you don't have to memorize them. But specifically, I wanted to look at the first one on the list, methyl orange. It turns out that both of the chemical structures you see on the top left side of your screen are methyl orange. The way it works is that indicators are these chemical compounds that have the ability to react with a proton. So the first thing I want to say is that these two substances are actually in chemical equilibrium with each other, and to balance the chemical equation, we have to add an H+. The H plus that's added, I don't know how well you all can see it in the structure, is right here. You'll notice that the structure on the left has an H plus attached to the nitrogen that isn't present on the structure on the right. Just one thing about these structures, obviously there's a lot of things missing. Each vertex, wherever all of the lines meet, each of these is supposed to be a carbon atom. We're not getting into organic chemistry today, but organic chemists, they all understand well enough when talking to each other that, hey, we can shorthand this even more to save some time. That's just something they do. The important thing to note is that we have this species here, HX. We can call it HX plus if we want to, because I see a positive charge there. And then this substance would then be called X. And then there's a hydrogen ion. And if you think about it that way, that kind of simplifies the chemical equation to you. I'm not really concerned about what this whole big methyl orange molecule looks like. What I need to know is that the only change is that it attaches an H plus. Interestingly, when that H plus is attached, it actually changes all the energy levels inside the molecule, and the visible light that's absorbed and released, to our eyes, we see red. When that H plus is not present, the electron energy levels all shift a little bit because an atom has left, all the bonded electrons shift into non-bonded pairs, a lot of stuff happens, but then this compound is yellow. And what's interesting is that since this equilibrium involves an H plus ion, the concentration of H plus ion is a stress. As H plus increases, there should be a shift in this equilibrium, and hopefully it's going to be a shift towards the left side. The idea being as pH goes down, the H plus concentration goes up, the equilibrium shifts left, and the solution turns red. As H plus concentration goes down, because pH has gone up, the equilibrium shifts right, and the solution turns yellow. And what's cool is that for each of these substances shown on table F, all 6 of them, there is an H plus concentration threshold where the color will change, where the equilibrium shifts. And as equilibrium shifts, as we've seen in other examples, color changes. So really this is an example of equilibrium, and it's an example of acids and bases because the H plus is involved. But the core idea is that if the chemical compound changes color when the H plus concentration changes, we just call it an indicator. And it's really nice that since you're given this table, that the end goal is just to be able to read the table and not to worry so much about the compounds, which is why I got rid of them. I mean, it's great to see the background, but like the execution's more important. So like I said, the H plus concentration, the critical H plus concentration, forgive me, I think I'm circling the right color change, is different for every compound. But when you have that compound and the information on the table, you can kind of reason it out. The way you read this table is that you line up the numbers on the left side of the range with the colors on the left side of the colors. In other words, for methyl orange, let me write that. For methyl orange, I'm abbreviating, if pH is less than 3.1, the solution will be red. And the idea is you actually get like a solution of something that you know, like a hydrochloric acid, a sodium hydroxide, a vinegar, and you take the methyl orange solution, you take the compound, you dissolve it into a second solution, and you take a dropper and you put in a couple drops. And then a couple drops is enough. You don't want to have too much of the indicator, because the indicator itself does interact chemically in an acid-base fashion. So you want it to be like present, but not the predominant source of all the chemistry that's going on. You just want it kind of there on the sidelines. If pH is greater than 4.4, the solution will be yellow. Now keep in mind, when you add that little bit of indicator, you're adding a constant amount or a fixed amount of methyl orange. So when you have the red form and the yellow form, obviously that's like the equilibrium position, like 10 to 90, 90 to 10. If for some reason the pH value is in the middle, well, you'd have comparable amounts of red and yellow, and to your eyes will just blend the two colors together. What you would get is orange. If you know the pH of the solution, you should be able to use table M to figure out the color that the indicator shown would turn in that solution. Go ahead and hit the pause button. Take a look at table M. For these 4 solutions, what color the indicator will show in those solutions. Bromthiamyl blue at a pH of 5.0. So bromthiamyl blue is the second one on our list. If the pH is 5, that is lower than the 6, where the yellow would start to turn blue or start to turn greenish. So we would say that this is yellow. In much the same way as we have this number line for methyl orange, as long as we're well past the lower point or well above the higher point, there's so much of one form of the chemical that you just see the one color. For litmus at a pH of 3.7, the tipping point is 4.5, so this is going to be red. For thymol blue, we're going to take a look down here, 8.0 to 9.6, we're at 10.3, so that's going to be blue. And bromcresol green at a pH of 4.6. Well, that one's in the middle. It's in between the two. Yellow, blue, well, I mean, I don't need too much of a color wheel. Green would be a good guess for me of what you're going to see, because you'll see some of the compound will be yellow and some of the compound will be blue, and so your eyes will like mix the two. Will be observed. There's the real power in indicators is not just to use them, but if you use more than one, you start to get some really good information about the actual, like the direct pH. You can actually, given these values, you can get very specific. So for example, I'm giving you a situation. One solution was tested twice with 2 indicators, 2 separate samples, indicators, different ones added to each sample. Adding phenolphthalein, you see that the solution stayed colorless. Adding bromthiamyl blue, the solution turned blue. Given that information, you should be able to give me a pH range that is not just like less than 5 or greater than 7, but specifically between 2 numbers and not just anything from that number down or up. Phenolphthalein, colorless, says the pH is less than 8. Bromthiamyl blue being blue says that the pH should be greater than 7.6. So that's kind of neat. If you test with a whole host of indicators, you get some very specific information, because now I know that this pH is somewhere between 7.6 and 8. Using 2 pieces of information gives you an order of magnitude more specificity than just using 1, because now you can actually really limit your pH. Now, depending on the 2 indicators you use, if I have an indicator where if I have 2 sets of data where it says like bromcresol green is blue and methyl orange is yellow, well, that's not really as helpful because both of them point to something greater than 5.4. But what I'm saying is, by using several indicators, you kind of get, you have a chance to zero in. So in summary, indicators change color, pH. The pH range varies from indicator to indicator. Is to read table M, because table M is always there, it's always available to you, and it will tell you what colors will happen and at what pHs they will happen. Thanks for watching.